Okay, next up on our minor component calculations list is going to be Rstr. So if you look in the glossary, Rstr stands for the maximum startup resistance to achieve the turn-on time target, also known as the VDD startup resistance. So what that is these resistors right here. So let me see, I think it might give us an equation for Rstr. Let me check here, so I'll just show you. So on the data sheet, I just Control F Rstr. So it does give us an equation. Okay, this is also interesting. We'll talk about it. So here you have this equation. So once this is known, the startup resistance from V-bulk to achieve the turn-on time target. So what this means is the turn-on time target. What that means is we pick the turn-on time of our system, and so that sort of basically leads to the question: well, what do we want our turn-on time to be? And this is kind of goes back to that story of the value judgment calls that engineers make. So what I could tell you from my experience is you might pick a turn-on time target that sort of meets industry standards, or say like other power supplies, like what their typical turn-on times are. You might pick a value based on some other constraints such as footprint size or BOM cost, or like maybe safety or something like that. There could be a lot of reasons why you would pick a certain start time. So to be honest, I don't really have an answer for what that number should be. But I think in the datasheet, it also mentions, if you scroll down, maybe it's up. Yeah. So if you look in the datasheet, this is just next one down. So I went up here and I just tabbed one down. Says typical startup resistant values for Rstr range from 13 mega ohms to 20 mega ohms to achieve 1 second startup time. So for that, I just kind of took it and ran with it. Said, okay, I guess we want our startup time to be 1 second, and so I picked a value of about 15 mega ohms. It's right in the middle. So, I just kind of went with it. So yeah, so it's pretty straightforward with that one. So the next one that we're going to take a look at is RPL. So if you look in the data sheet, RPL stands for the preload resistance on the output of the converter. So basically it's that resistor that was in parallel with the capacitor on the output that you might have seen. So they give us a pretty straightforward equation to follow, and that is VOCV squared divided by PSB underscore converter minus 2.5 milliwatts. So if you look in the data sheet, if you just Control F for PSB underscore conv, it tells you that it's equal to 30 milliwatts. So you can find it. So if you just plug in these numbers, you get a value of RPL of around 909 ohms for that output. So yeah, it's extremely straightforward right there. In here, I guess we'll even talk about this one. So RCS, if you remember a while back, we actually solved for this value already during the major component calculations, and this was in order to calculate our primary inductance. So let me just, hopefully this will refresh your memory. It's the primary current programming resistance. So if you look here, it talks about this. RCS, so it gives us the equation. So hopefully this should look familiar too. That is what I put for that. So yeah, that's what I put for RCS right there. So that should cover it for the next phase of components I want to cover. Next, I'll just kind of keep working my way. Well, actually, we can keep going. We have more time than I thought. So the next one up is going to be RS1. So if you look on the data sheet, RS1, I think this is also, oh yeah, so this is referred to as RS1. So RS1, it gives us the equation V in run times square root of 2 divided by N sub PA times I VSL run. So NPA is equal to 3.75. And I don't know why I put volts here because that's not a voltage. It's a winding ratio. So this is the primary to auxiliary winding ratio. And in this case, the value I chose was 3.75 because I think it was just, again, like I did the calculation and I just kind of looked at it and picked something with a little bit of headroom there. So V in run, this value is referred to, this is like the brownout voltage. You find this in a table, and it basically, you just pull it from the table. It's 70 volts. And then the same thing for IVSL run, you can pull that from the table. It's 220 microamp. So whenever you do the calculation for this value, it spits out a value of 119.98 kilo ohms. So I guess this is also a good time to mention that when it comes to sourcing resistors like this, like when you start shopping, you're not going to find something that is exactly 119.98 kilo ohms. You're going to try, you might find something that's like 121 or 120. So I would say try to get it like as close as you can, like just round a little bit. So like find something that's like 120, 121, something like that. And you should be okay right there. I think it'll be just fine. But yeah, so that's don't get too granular with these choices. So that's kind of what I'll say about that. So the next one up is RS2. So yeah, quickly I can also show in the schematic. So this is like RS1 and RS2. Ooh, I think I made a mistake. These aren't supposed to be the same. But one of these is supposed to be RS1 and one of these is supposed to be RS2. I think this one's supposed to be 28 kilo ohm one. So this is it should be the 28. See, even engineers make mistakes, guys, and that's also a mistake too. What was this, 105? Here, we'll figure out which one it was. 108, okay. Here we go. I think that's what it was from memory, but actually, honestly, I could just look down here. Yeah, so 27.11. So again, it's pretty straightforward again with this equation. So basically, if you don't know, what we're doing is we're creating a voltage divider across this output. This looks very familiar. So you have ground right here, then you have your input voltage right here. And this basically creates a voltage divider between this and ground. I actually don't know what the voltage divider multiplier is because it didn't really matter that I know it because it just tells me the values that these should be. So again, we're going to plug into this equation. We have RS1, which we just solved for up there. And then we have V sub VSR. So if we look in the data sheet, let's see if we can tie that on. So V sub VSR is the CV regulating level at the VS input. So it says C electrical characteristics table. So you just solve, you just look up that value. It's in the table. Maybe we can even go to it. Yeah, if I just click on that blue link, it sends us up here to V sub VSR, and it just tells you value. And I think I chose 4.05 volts. VOCV, that's our output selection, 5 volts. VF is equal to 0.9 volts. So what that gives us is a value of 27.11 kilo ohms. So if you can see, what I ended up choosing was 28.7 because that was like a nice round number that I could find that was just pretty easy. And I think I used reference schematics for that choice as well, just to compare my answers to. But note that we have an idea that we're doing it correctly because we're very close to what these other values were. Fact, see. Yeah, I think we were fine on. So yeah. Here we can continue on because we still have time. So the next value up is the RLC value. So if you look in the data sheet, the RLC value is referred to as, I don't think it actually lists its name in the glossary. I'll just show you one. Okay, so if we go down to the glossary, we look at the resistor values. Oh, we gotta go back up. Rlc. So it looks like it skips it, but we can still find it by control Fing. So the can maintain constant current regulation by utilizing line compensation. So this sounds like it stands for line compensation. So resistor sub line compensation. It's really interesting to note though. This value should be this term should be defined in the glossary, and I don't know why it is. So just know, like, even engineers at TI make mistakes. Just get used to that. I'll say a lot, especially when you're reading through data sheets. It annoys me a lot when they just miss little details like this. So anyways, yeah, so it gives you these values, or it tells you RLC is equal to, and I have the equation K sub LC times RS1 times RCS times T sub D times NPA over LP. So it gives us we already have LP because we solved for that value. T sub D, let me see if I can find if it mentions what T sub D is. T sub D is the current sense delay, including MOSFET turn off delay. Add 50 nanoseconds to MOSFET delay. So I think what I did with this one was I went and looked up the data sheet for the MOSFET that I sourced. I don't have that data sheet on hand, but I just looked at the turn off time, and that's listed in the MOSFET's data sheet. And obviously, if you can do math, you know it was around 23 nanoseconds for the turn off time of the MOSFET. So that gives you a value of 73 nanoseconds. Then for K sub LC, K sub LC is the current scaling constant right here. So it says refer to the electrical characteristics table. So I just picked the number in the middle, which was 25. So that should give us pretty much all the values we need. I forgot to list NPA, but we already listed it up here as 3.75. And whenever you plug in all these values, you get a value of 1,723 ohms. So again, try to shop for something that's a little bit close to this. It doesn't have to be exact, but something right around this. So with the conclusion of solving for this value, that we're actually done now with all of the minor component calculations. So referring to my little flow sheet here, granted, you know I'm filming this video out of order, but know that next up is going to be the actual schematic capture. So I'll kind of just take you through that part and walk you through kind of how I do that. It's pretty self-explanatory, but just so you can kind of see things, how I do them, I figured I wanted to feature it. So yeah, that's going to be the next part up. So thank you so much for sticking it through with this. I really appreciate everyone who's watching these and putting up with my shenanigans. So thanks.